Everybody, we're going to start with the second half of 10, and what we're going to be looking at is hybridization. Okay, so I'm going to pull this up. Remember the very end of, General Chemistry 1, we went over shapes and everything, okay? Well, this is something similar, kind of goes along with it. What we're going to do is look at the orbitals that are involved in the shapes, if you want, okay? So there's a valence bond theory. So remember, just a quick review, orbitals are where the electrons are located. Remember there's different shapes. So the S shape is like a sphere, the P is like a figure 8, the D is kind of like an X, and the F is like an X, but going up and down. Anyway, just crazy. Anyway, so they're just like the general area, the general space where the electrons are located, the three-dimensional space. Okay, what they found, according to the valence bond theory, is that more than likely these orbitals don't just exist by themselves. That really what you're getting is a hybridization of them, meaning they're going to mix together. So you don't just have an s orbital, you have like an sp orbital, meaning the orbital where that electron is located has a little bit of s character, a little bit of p character. Okay, and so let's see what that looks like. Okay, basically what we're going to look at is when things need to be hybridized. This example might confuse you, so let's actually just go on to hybridization. Okay, when you hybridize, basically when you combine orbitals together, okay, so shapes, when we combine the sort of shapes together, it's because you want to maximize the bonding, okay? So there's basically more electron density. You know, electrons, because that's what's involved in bonding, and density just meaning there's more energy involved in that orbital. So if we combine an S and a P, does it make sense there's going to be more electron energy or density than if you just have an S or if you just have a P, because now we have a combination. And so we're trying to maximize the overlap of these orbitals. So we're going to overlap the electrons because that's what causes bonding. Okay? So let's look at the example of CH4, and maybe this will start making sense. So what I'm going to do, I'm going to do a lot of examples, and I'm going to derive these hybridizations for you just to show you where they came from, but then I'm going to show you the shortcut. And so really you need to know how to do the shortcut, but I need to show you the long way first so you understand where the shortcut came from. Okay, so let's look at this. We're going to look at CH4. Okay, so I'm going to come over here and start drawing. So I have CH4. Now what I need to do is the electron configuration of all of these. So I'm going to look at carbon. This is my central atom. Okay, remember this is, I'm just going to look at the valence part of it. 2s2, 2p2. So if you want helium, if you really want to get specific, but really we're just looking at the valence, so it doesn't matter that much. So let's look at the arrows now. S, there's 2 of them, so we'd have 1, 2, and the P, we have 3 lines. We have 2 arrows because the 2 right there, so 1, 2. Okay, how many unpaired arrows do I have? Do you see that I only have 2? These 2 arrows are paired up, but these 2 are not. So I have 2 unpaired. Okay? And to be able to bond with something, you have to be unpaired, okay? These are paired up, so they can't bond, but these 2 can. Now let's look at the hydrogens. There's 4 hydrogens, okay, but let's just look at one of them. That would be 1s1, okay? 1 line for the S, and be 1 electron. Okay, but there's 4 of them, right? So it's like times 4, so if I just draw all 4 of them really quick. 1, 2, 3, 4. So this is, because there's 4 hydrogens, because you see it's CH4. Okay, now all of these 4 hydrogens here, if we add all of the unpaired arrows, how many do we have? Do you see that we have 4? 1, 2, 3, 4. Okay, now again, going back to the valence bond theory, you need to maximize the unpaired arrows because the unpaired arrows are what causes bonding. Okay, but if we look at carbon, because you see the hydrogen is bonded to carbon, and it's ground state here, how many ampere do I have? We said 2. So does that match up? We need 2 ampere, but how many do we have? 4. Okay, so that doesn't work. So basically what the valence bond theory says is that we're going to hybridize. So we're going to mix orbitals. Hybridize the orbitals. So we're going to mix them. Okay, so imagine we put them in a blender. We have, let's see, SP. Okay, so we're going to have one S, okay? And then we have 3 P's, right? Because there's 3 P shapes. Okay, so I'm going to mix these up in a blender. So now I'm going to have a mixture of sp3s, right? Because I'm mixing them together. But how many would I have? All right, and this is what we look at. Do you see how many lines there are? How many lines did I draw total all together? I have 1, 2, 3, 4. Okay? So I draw my 4 lines over here. I mix all those 4 lines together. So I mixed 1, 2, 3, 4. Those are my possible orbitals. And I mix them all together like I would cookies. Now I'm scooping them out. Now I have an sp3 mixture right here. Think of that as like a chocolate chip cookie. I have a chocolate chip cookie there. A sp3 chocolate chip cookie there. An sp3 chocolate chip cookie there. And an sp3 chocolate chip cookie there. Okay, so now how many lines, now this is my new orbital, how many lines do I have? I have 4, okay? So think of this, you see how the P has 3 lines to it? Now these sp3s have 4 lines on them. Okay, now how many electrons do I have to work with in the valence shell? How many valence electrons does carbon have? If you look, it has 4 valence electrons. Okay, so I'm going to put those 4 valence electrons in my new sp3 orbitals. I'm not going to pair them, right? Because I'm going to unpair them first. Now look, how many unpaired electrons do I have? 4, which is what I need right here. I need 4. So this is called a sp3 hybrid orbital. So I combine the s, 1s and 3 p's to make a new orbital so that I can have 4 unpaired electrons. Okay? I hope that makes sense. So again, there wasn't enough unpaired electrons for carbon to efficiently bond with hydrogen because it needed 4. So what it did, it mixed all of its valence orbitals together and then re-entered the electrons, so now it has the 4 unpaired like it needs. So anytime you need to do this, anytime you need 4 unpaired electrons basically like this, that will be sp3. Okay, so now let's look at sp2. And again, I'll show you a shortcut so you don't have to derive it each time like this. Okay, so let's look at sp2. Okay, let's look at the example they have here. They're looking at BH3. Okay, so let's look at BH3. BH3, and I'm going to tell you right now, this is going to be sp2. So let's see how this is sp2. Okay, so again, we're going to start the same way. We have boron. Okay, and this is going to be a 2s2, a 2p1. Okay, s, my p's, 1, 2, 3. Okay, now how many valence not valence. So I have 2 electrons here, so 1, 2. I have 1 electron here, so 1. So how many unpaired electrons do I have? I have 1 unpaired, 1 unpaired. But let's look at how many we need. We have 3 hydrogens. There's 3 of these, and again, this is going to be 1s1. So each hydrogen will look like this. So there's 3 of them, so I'm going to say 1, 2, 3. So these are each the different hydrogen atoms. This is a different hydrogen, again, because there's 3 of them. So I have 3 unpaired electrons. Okay, do I have 3 unpaired electrons here, or arrows? No. So what do? I hybridize them. Okay, now how many do I need? I need 3, right? Okay, so you always start with the lowest first. The lowest is always the S. So S. Now how many P's do I need? I only need 3 total. So I have an S orbital. I need 3, so I need sp2, right? I have 2 P's, 1 S, that means 3. Okay, so I have my sp2 line, sp2 line, sp2 line. And again, I know I need 3 because I need 3 unpaired arrows. So I'm going to combine 1s and 2 p's. So I'm combining a total of 3 orbitals. Okay, now how many valence electrons in boron? 3. So it'd be 1, 2, 3. Now it works perfectly. Now this sp2 orbital has combined together to increase the electron density, or like the unpaired electrons. So now it can bond with the 3 hydrogens efficiently. Okay, so that's why BH3 is sp2. Okay, now let's look at sp. And they're doing it doesn't say which one they're doing here. So let's make up an example. Oh, they're doing beryllium. So beryllium H2. BeH2. So again, we'll look at beryllium, which is going to be 2s2. Okay, then we're going to look at the hydrogens. There's 2 of them. We've done hydrogen to know that they're going to be 1s1, and there's 2 of them, so there's actually 2 unpaired arrows because there's 2 hydrogens. Okay, now we're going to do beryllium. We have 2 electrons there, so one going up, one going down. Okay, this needs 2 unpaired electrons, right? But how many do we have? 0. 0 unpaired electrons. They're all paired up here. Okay, so what do we need to do? So we go in order. So when we combine these, we have, this is how it goes. We have 1s, we have 3 p's, and D we have up to 5 if we need it. Okay. We need to combine 2. How do I know we need 2? Because we need 2 unpaired arrows. So first we're going to use an S. Okay. That only uses 1 orbital. How many are we going to combine? 2, because we need 2. So we're going to have sp and sp, again, because we need 2 unpaired arrows. So we combine 2 orbitals to make 2 new orbitals. And now beryllium is in group 2, so it's 2 unpaired electrons, or 2 valence electrons, which I could put here and here. So now beryllium can bond with hydrogen. So when beryllium bonds, it's going to bond with these hybrid orbitals, basically these mixed orbitals, instead of just like 1s. Okay, it's not, anyways, again, to maximize the bonding. Okay, so we've looked at, again, to remember, an sp3, an sp2, and an sp. So again, let's just see what this means again, and I'll show you again a quick and easy way to derive this easily. So if you have sp3, that means you hybridize 1 s orbital and 3 p's to maximize bonding. If you have an sp2, you hybridize 1 s and 2 p's to maximize bonding, and if you have an sp, you hybridize 1s and 1p to maximize bonding. Okay, so this is just what you needed to maximize bonding. So max bonding, basically the strongest bond. Okay, now let's look at the next one. Okay, and they have an sp3d. Okay, and they looked at P 1, 2, 3, 4, 5, PCl5. Okay, so we have PCl5. And this is going to be an sp3d. So I can tell you right now that they're going to combine 1s, 3 P's and 1 D. That's what they're going to hybridize so you can maximize and make the strongest bond. So let's look at why. Okay, let's look at phosphorus. Let me pull the periodic table so you can see it. Phosphorus is right here. So this is going to be 3s2, and this is the valence. 3s2, 3p1, 2, 3. Okay, so I have 3s2, 3p3. So this is going to look like this. 1, 2 for the s, and for the p's, 1, 2, 3. Okay, if we look at chlorine, chlorine is going to be, I think it's, let me just show you, right here, 3s2, 3p1, 2, 3, 4, 5. Okay, and there's 5 of them, remember, so just pretend I'm doing this 5 times. So 3s2, 3p5. So my S will look like this. They're both paired. 2, 3, and 1, 2, 3, 4, 5. So how many unpaired electrons right here for this one? I have 1 unpaired electron, but I multiply that by 5 because there's 5 chlorine, so really I have 5 unpaired. Okay, now let's look at this. I need 5 unpaired because that's what would maximize the bonding, make the strongest bond. But how many do I have in phosphorus? 3, okay? Because it's always your central atom that hybridizes. So phosphorus actually needs 3. So we're going to combine 3 orbitals, 1 s, 3 of the p's, and 1 d. Okay, so we count 3, 4, 5. 5 total. So how many lines do you think we're going to make? 5. 1, 2, 3, 4, 5. So these are all sp3d. I'm just going to go, well, all of them are sp3d. Now, how many valence electrons in phosphorus? I bet you can guess 5. 1, 2, 3, 4, 5. So now, when I make this new hybridized orbital, I can have 5 lines, so I can have 5 unpaired electrons to bond with these chlorines. Okay, and then let me show you the last one, which is going to be sp3d2. They say SF6. Okay. SF6. Oops. 6. So if we look at sulfur, this is going to be 3s2, 3p4. So 1, 2 for the s's, 1, 2, 3 for the p's, 1, 2, 3, 4. Right? So only 2 unpaired. But can you imagine? Can you think? How many unpaired do you think these fluorine will have? 6 total. Fluorine will have 6 because there's going to be 6 unpaired electrons if you do it. Okay, so I need 6, but how many do I have? I have 2. Okay, so I need 6 orbitals to combine. So I'm going to combine 1s, 3 of the p's. Okay, that gives me a total of 4. I need 2 more. So I'm going to do 2 d's. So sp3d2. All of these are going to be sp3d2. And I'm going to have 6 of them. 1, 2, 3, 4, 5, 6. How did I know 6? Because I combined 6 orbitals. And how many valence electrons does sulfur have? 6. So 1, 2, 3, 4, 5, 6. So these hybridized orbitals basically allow you to maximize bonding, make the strongest bond by unpairing all your electrons, because electrons have to be unpaired to be able to bond. So what orbitals do for this to happen is that they actually will hybridize together to make sort of this new bond. Okay, now let me show you this chart. Oops, that's not the chart. Right here. This chart shows you everything, and these actually go with the shapes. Okay, The electron shape. Let me go to maximize this. So anytime you have a linear electron shape, you're always going to be sp, hybridization. If you have a trigonal planar electron shape, now again, not the molecular shape, but the electron shape, this is an sp2. Tetrahedral is always sp3. Trigonal bipyramidal is sp3d. And octahedral will always be sp3d2. Okay, so let's escape. Let's do some examples. Okay, let's do like NH3. NH3. Now what I would do, okay, well, let me also put this. So we're going to do, there's SP, SP2, SP3, SP3D, SP3D2, okay? So now let's put orbitals. So how many orbitals were involved in the hybridization, okay? So for this first one, we have an S and a P, okay? So we have two total, one S, one P. Here we have one S and two P's. That's a total of 3. SP3, 1S, 3P, so this is 4. And here we have SP3 plus D, so that'd be 5. And this last one will be 6. Okay? Now let me get a different color. Let me use, I guess, this orange here. Now let's look here. Now we're going to circle everything coming off this nitrogen, including lone pairs. So I have a hydrogen, a hydrogen, a hydrogen, and a lone pair. Okay? So how many total things are bonded or possibly bonded? Because if you have a lone pair, that means it's a possible bond. Okay? So how many circles basically do I have? Do you see I have 4? So I come over here. How many orbitals do I need then? 4. This will always match up. So however many circles you need, that's how many orbitals you need. So this one is sp3. Okay, let's look at another one. I, Cl, 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 lone pair there, lone pair there. Okay, I'm going to change my color. Okay, so I'll make a circle around chlorine. Chlorine, I have a lone pair. I have a chlorine, I have a chlorine, and I have a lone pair. So how many total did I make? 1, 2, 3, 4, 5, 6. 6 circles, that means I need 6 orbitals. So this is sp3d2. Okay, let's do another one. Let me think. Let's do H, C, H, double bond oxygen. And let's do the hybridization of carbon and of oxygen here. Okay, so let me change the color to, I guess, this green color. So let's do carbon first. Carbon, directly coming off carbon, I have a hydrogen, and an oxygen. Okay, notice I didn't make 2 circles around oxygen because that's double bond. I just made 1 because there's just an oxygen coming off. So how many total? 3. So I come up here with 3, that is a sp2 for the carbon. Okay, now let's look at oxygen. Let me do this a different color. Let's do this maroon color. Okay, oxygen here has a lone pair, and a carbon. Okay, so how many reddish ones do I have? 3. So oxygen is also sp2 right here. Okay, so I hope that makes sense. That's the kind of the shortcut, easy way to do this, so you're not deriving it. I just wanted you to see where it came from. So basically, when you say, oh, that's sp2, you're saying that that's the orbitals you have to combine so you have the maximum number of unpaired electrons to bond. Okay, let me show you this one last thing. And this, I'll get a new one. Okay, So let me show you double and single bonds. So we have an SP, SP2, SP3. Okay? Anytime, these tell you how many single bonds. So what's the best way to do this? Okay, let's think of this. Okay, there are a total of 3 p orbitals. Okay, so there's a total of 3 p's. Okay, so let's count the leftover here. Did I use 3 p's in this one? Or actually, let's start down here. Did I use 3 p's? Yes. So are there any leftover p's? No. So no leftover p's. So I'm putting, the p's left over. Basically, what did I not use? Okay, now let's look at this one. I only used 2 of the p's. So are there p's left over? Yes. How many? 1 p. And over here, I used only 1 p. So how many left over? 2. Okay, leftover is another way of saying unhybridized. Basically, I didn't mix it. Okay, now when you get your multiple bonds, there's double, single, triple bonds, we'll say. Now let's look at here. Let's do a different color. Let's go to this purple. Okay, now let's look at bonds. Okay, to get a multiple bond, you need an unhybridized p. So multiple bond equals unhybridized p. Okay, so this one here says there's no unhybridized p, basically no multiple bonds left over. So the answer here is 0 multiple bonds. Okay, this one here, how many extra do I have? I said I have 1, so I have 1 multiple bond. And then here I have how many extra? 2. Okay? Now what do we do? Now to have your extra bonds here, so let's look up type. Okay? This one has 0 multiple bonds. Okay, so that means it's a single bond. This one has 1 additional bond or a multiple bond. So everything has a single bond because that's how you have a bond. So this one has an additional bond, 1 additional, so like this. So this one is actually this could be a double bond. Now this one I have 2 additional bonds, so I have my single bond. And I have 2 additional ones, so how many do I have? 3. So this is a triple bond. Okay, so what does this mean? This means if you have, so a single bond just means, like sp3 or whatever. A single bond is not as important. But for the double and triple bond, it's a little more important. So a double bond is always going to have an sp2 hybridization. And a triple bond will always have an sp hybridization. So if I'm looking at something, like this long carbon chain, I don't know. And let's just, wait, sorry, you won't know what that means. CH3, CH2, C, triple bond, CH. Okay, and I say, what's the hybridization of all the carbons? Okay, now let's not worry about it so much right now, but let's look at right here. Okay, do you see that both of this carbon and this carbon are attached to a triple bond? So that means that this is going to be sp. Okay, because it has 2 extra bonds. Besides that single bond, so it needs 2 leftover p's, so it has to be sp. Now, if it was a double bond instead, so let's say like CH2 double bond CH2, now these 2 carbons right here are going to be sp2 hybridized. Okay, so basically anytime you see a triple bond, the bonds attached to it are sp. And if you see a double bond, the bonds attached to it are sp2. So try to do some examples and see if you can figure out the hybridization.